So, here's a huge question for you. In a world with countless variables, everything from our genetics to our lifestyle, how on earth do doctors predict survival? It seems almost impossible, right? Well, today we're going to pull back the curtain and find out exactly how they do it. And that right there, that's the core of the problem. Every single one of us is this unique mix of risk factors and, well, protective factors. Statisticians have a word for this, heterogeneity, but really it just means everyone's different. And that makes creating a one-size-fits-all prediction incredibly tricky. I mean, just look at these two people. Intuitively, you and I both know their risk profiles are worlds apart. But by how much? Is patient B's risk twice as high, 10 times higher? And maybe more importantly, does that gap in their risk stay the same over the years? To even begin to answer that, we've got to break the problem down into its parts. Okay, so to get our heads around this, we need to start with the building blocks. Let's talk about what these individual risk factors are and what statisticians aren't really talking about when they use the word hazard. So first up, we have this thing called covariates. It sounds technical, but it's just a label for all those measurable things we mentioned. I love this analogy of thinking of them as a panel of risk dials for every single person. You've got a dial for age, another for blood pressure, one for the kind of treatment you got, and each person's dials are set to their own unique values. And then there's the second key idea, hazard. Now, don't get this confused with the overall chance of something bad happening. It's way more specific. Hazard is the immediate, right-this-second risk of something happening on the condition that you've made it this far. It's a constant, moment-to-moment measure of your immediate danger. You know, for the longest time, the real head-scratcher was figuring out the basic shape of that hazard over time. Before you could even think about adjusting all those individual risk dials, you first had to guess the fundamental curve of the risk itself. So what did they do? Well, the early models, they basically tried to guess. They try to fit all the data to a pre-selected shape. For example, maybe the risk is just constant. This flat line here shows a steady, unchanging hazard. Think about the daily risk of getting into a car accident. It doesn't really change dramatically from one day to the next. Or, hey, maybe it's the other way around. Maybe the risk starts super high and then drops off. This is really common for someone recovering from a big surgery. Your risk of a complication is highest right after the procedure, but with every day you recover, that hazard goes down. And then, of course, you've got the total opposite, a risk that is always going up. This is probably the one that makes the most sense to us, right? It perfectly mirrors the risk of dying from natural causes, which, unfortunately for all of us, just keeps climbing as we get older. And one last one for you. You can get this kind of humped risk. Here, the hazard starts low, shoots up to a peak, and then starts to fall again. You could use this to model an acute illness, where the danger is highest for a few critical days, but if you can just get over that hump, your risk starts to drop off. So you see the problem here, right? All of these early models, they're called parametric models. They forced you to pick one of these shapes before you even started your analysis. And if you guessed wrong, say you picked a decreasing risk model for a situation that actually had an increasing risk, well, your entire analysis, everything you found could be just flat out wrong. This was a huge problem. And this huge problem is what sets the stage for a real breakthrough. It came in 1972 from a statistician named Sir David Cox. And his idea was so elegant, so powerful, that it completely took over the entire field of survival analysis. I mean, our source material for this explainer puts it perfectly. The main problem was that if you chose the wrong shape, your whole foundation was flawed. How could you ever hope to measure the effects of risk factors if your basic assumption about the shape of that risk was wrong from the get-go? And this is where the Cox model is just brilliant. It came up with a way to neatly separate the two things we actually care about. The big idea was, let's stop worrying about the underlying shape of the risk. Let's just forget about it. Instead, let's build a model that focuses only on one thing, measuring the strength of those individual risk dials. So here's how it works. The model basically splits the whole idea of hazard into two clean pieces. First, you have what's called the baseline hazard. Think of this as the underlying risk curve for some hypothetical average person. And this is the magic trick. The Cox model says we don't even need to know what this shape is. It doesn't matter if it's increasing, decreasing, humped, whatever. It just treats it as an unknown. And the second piece of the puzzle? That's the proportionality factor. This is just a single number, a multiplier, that gets calculated from a person's specific risk dials, their covariance. This number then takes that unknown baseline hazard and just scales it up or down. If you have a bunch of risky factors, your multiplier is bigger than 1.
If you have protective ones, it's less than 1. Simple as that.
And that is why they call it the proportional hazards model. You can see it here perfectly. Both patients are following that same unknown underlying risk shape, but patient B's curve is just consistently scaled higher than patient A. If their risk multiplier is 1.5, their hazard is always 1.5 times higher at every single point in time. The ratio of their risks is constant. It never changes. Okay, that's the theory, but let's look at a real-world example to see how this actually works in practice. How does this let us decode the actual impact of different risk factors? Let's check out a study on heart surgery patients. The model uses what are called dummy variables, which are really just simple on-off switches, a 0 or a 1. In this case, our baseline group is a female patient at Hospital A. See how all her switches are set to off? Now, for a female at Hospital B, you just flip the Hospital B switch to on. For a guy at Hospital C, you flip both the male switch and the Hospital C switch on. So when they ran the numbers, the model let them cut through all the noise and isolate the effect of just the hospital. And what they found was that, after accounting for things like gender, patients at Hospital A had a 2.53% higher mortality risk than similar patients at Hospital B. This is the power of the model. It lets us quantify that difference to see if one treatment, or in this case one hospital, is genuinely better than another. All right, let's bring it all home. Why did this one statistical model become so incredibly important in modern research? What makes it so special? It really all boils down to these 4 things. First, it's flexibility. By not forcing a guess about the shape of the risk, it sidesteps that massive problem from the old models. This lets it focus on what we really care about, isolating and measuring the impact of each risk factor. That gives it the power to make these direct comparisons, to say things like, this new drug reduces the risk by 30%. And because of all that, it's become the absolute foundation of this work, the first tool pretty much any researcher grabs. And that kind of leaves us with this one big forward-looking question, doesn't it? The Cox model was a game changer for analyzing risk for specific events. But as we collect more and more data on ourselves, from our genomes to the number of steps we take each day, what's to stop a similar, more powerful model from one day calculating a personalized risk profile, not just for one disease, but for our entire lifetime? It's a pretty powerful thought. Thanks for diving into this with me.